Hi class, more linear algebra. We spent the last few videos exploring elementary matrices and their determinants. So let E1, E2, and E3 be n by n elementary matrices of types 1, 2, and 3, respectively. Here's something that we know. If A is an n by n matrix, some other matrix, we know from our various claims that the determinant of E1A is negative the determinant of A. Multiplying by a type 1 matrix negates the determinant. And the determinant of E1 itself is negative 1. We know that the determinant of E2A is alpha times the determinant of A. This is when E2 scales a row by alpha, then it will scale the determinant by alpha. In this case, the determinant of E2 itself is some alpha in the reals, non-zero alpha in the reals. The determinant of E3 times A is the determinant of A, and the determinant of E3 itself is 1. Notice, if E is an n by n elementary matrix of any type, and A is some other n by n matrix, what we've actually shown, amongst other things, is that the determinant of E times A is simply equal to the determinant of E times the determinant of A. Let's use this. But first, I just want to remind you of Theorem 5. Again. If A is, of course, our n by n matrix, then the following are equivalent. 1, A is non-singular, as in A has an inverse. 2, the equation A times x is equal to the 0 vector has only the trivial solution. And 3, A is row equivalent to the n by n identity matrix. Now let's prove the thing that we have been basically working up to for quite some time now. Theorem 18. If A is an n by n matrix, A is singular if and only if the determinant of A is equal to 0. Proof. Here's something that we'll know. That A is going to be row equivalent to some matrix in reduced row echelon form. Reduced row echelon form. Since every matrix via elementary row operations can be reduced to such a matrix. Here's something that I want you to remember, that when we do our row operations to reduce our matrix to reduced row echelon form, each one of those elementary row operations can be represented by left multiplication by an elementary matrix. So U is going to be A after it's been multiplied by a bunch of elementary matrices. So let's use what we've learned above. If I take the determinant of both sides, and I use the fact that the E sub i's are elementary matrices, I can break this determinant up. Here's what I want you to realize. The determinant of an elementary matrix is either 1, -1, or some alpha, which is a non-zero scalar, a non-zero real number, which means while I don't know what all of these determinants are, I know that this is a non-zero scalar. And here we have the relationship between the determinant of U and the determinant of A. The determinant of U is going to be 0 if and only if the determinant of A is 0. This is what we're going to use to prove the rest of this theorem. If A is singular, then U, which is its reduced row echelon form, is not the identity matrix. U has to have a row of zeros. Since it has a row of zeros, its determinant is 0. And this implies, as we showed above, that the determinant of A itself is 0. Let's do the second case. If A is non-singular, well, by Theorem 5, the reduced row echelon form of A is the identity matrix. That means that the determinant of U is 1, and because of the relationship between the determinant of U and the determinant of A, the determinant of A is certainly not 0. End of proof, QED. Putting this all together, we can now update Theorem 5. Theorem 19. A is an n by n matrix. Then the following are equivalent. 1. A is non-singular. 2. AX is equal to the 0 vector, has only the trivial solution. 3. A is a row equivalent to the identity matrix. And 4. The determinant of A is non-zero. Here's an exercise for you. Establish the following. Lemma 20. Let A and B be n by n matrices. If B is singular, then A times B is also singular. This lemma is going to help us prove what's next. Here's a question that you might have. Question. If E is an elementary matrix, then we know that the determinant of EA is equal to the determinant of E times the determinant of A. Note, this is something that might require some thought. The same is true on the right, that the determinant of AE is equal to the determinant of E times the determinant of A times the determinant of E. You might also ask yourself, does this equality work for non-elementary matrices? The answer is yes. Theorem 21. If A and B are n by n matrices, no matter what kind of matrices these are, if the determinant of A times B is equal to the determinant of A times the determinant of B. Proof. Much like the last theorem, we're going to break this into two cases. If B is singular, then, by the lemma that you will prove, A times B is singular. So the determinant of AB is equal to 0. Why? By theorem that we proved above, Theorem 19, or 17, depending on what you, or 18, depending on what you want. This also means that the determinant of A times the determinant of B is 0, since the determinant of B is 0. So the determinant of A times B is equal to the determinant of A times B, times the determinant of B. Next case, if B is non-singular, then by Theorem 5, B is row equivalent to I, as in B is equal to I after some elementary matrices have multiplied on the left. Since I doesn't change a matrix via multiplication, B is this product of elementary matrices. So notice, the determinant of A times B is going to be equal to the determinant of A times E1 through En. Since these are elementary matrices, we can break this determinant up. However, this also means that we can put some of them back together. Which gives us the determinant of A times the determinant of B. We have a lot more to talk about, but for now, just think on what we've done. QED, end of proof, end of lesson. See you next time.